So hello everyone. In this particular video, we will see what do we mean by orthogonal vectors or orthogonality. For this, we will consider example. Here we have two vectors, v1 and v2. And we say that vectors v1 and v2 are orthogonal if both the vectors make 90-degree with each other. That means they are perpendicular to each other. Perpendicular to each other. Okay. The other way of finding the other way or we can say the way to find whether a vector v1 and the vector v2 or two vectors are perpendicular to each other or not, we do that by finding the dot product of those two vectors, and if the dot product is 0, then the vectors are said to be perpendicular to each other or at 90 degrees. And a set of vectors where we have all the elements, that is the elements are the vectors and all the vectors are orthogonal to each other, then the set is called orthogonal set. So in case of a 2D space, we have only two vectors in the orthogonal set, v1 and v2. In case of three-dimensional space, we will have three vectors, v2, v3, and similarly in case of n-dimensional space, we will have n vectors. Now, when we will say that these are orthogonal or this set is an orthogonal set, then V1 should be perpendicular to V2, V2 should be perpendicular to V3, and V3 should be perpendicular to V1 also. So this is what we call as mutually orthogonal, mutually orthogonal to each other. Okay, so in this particular example, we are taking two vectors in two-dimensional space, and for the ease of understanding, we are taking two vectors. One is along the x-axis, and we call it v1, and one is along the y-axis, and we call it v2. And we have to note that the orthogonality between two vectors or two vectors being orthogonal is a concept that requires both the vectors to be present in the same coordinate frame. A particular space, let's say this is a two-dimensional space, so it can have multiple frame of references. Let's say this one is x1 y1, so we can have a different frame also which is x2 and y2. In this case, if we are talking about the orthogonality of the vectors, then both the vectors v1 and v2 should be in the same reference frame or same coordinate frame. They should not be represented in different coordinate frames. So this is one condition that we should keep in mind. Now in this case, this is the coordinate frame. Let's say this is x1 and y1, and we have two vectors v1 and v2 presented in this same coordinate frame, and both the vectors are 90-degree. And this we know that the x and y, the coordinate axes are at 90-degree. Therefore, uh, these vectors are at 90-degree because these vectors are parallel to the coordinate frames. But how do we find this mathematically? That both the vectors v1 and v2 are at 90-degree. For that, we will use the dot product. We will use the dot product of the vectors, and if we get 0, then the vectors are orthogonal to each other. So the conditions that we should keep in mind is that both the vectors v1 and v2 should be in the same coordinate frame, and we check the orthogonality by finding the dot product of the vectors. So we may not be having a graphical representation of the vectors, uh, and we may not be able to clearly state whether the angles are 90-degree or not just by looking into a graphical representation which is above three dimensions. So in that case, what we can do is we simply find the dot product of the vectors presented in any space, and if it comes out to be 0, then those vectors are orthogonal to each other. That means they are perpendicular to each other, or they form 90-degree between each other. One important point is that a zero vector is always orthogonal to every vector. Why so? Okay, so we said that the dot product should be 0. Dot product should be 0. So dot product of any vector with 0 vector is always going to be 0. Is always going to be 0. This can be verified by the formula how the dot product is calculated, which is like this. So dot product of any vector with zero vector is always going to be zero. Therefore, it means that zero vector is always going to be orthogonal to every vector. What it means is that zero vector is always perpendicular to every vector within the same coordinate frame. So zero vector should also be in the same coordinate frame. As an example, we will take these two vectors v1 and v2 represented in x and y in this particular coordinate frame, and we do not know what is the angle here. It looks 90 degree, but we are not sure whether it is 90 degree or not. Then what we do is we find the dot product. Dot product is this. It is the summation of the product of individual elements of the vectors. In here, what we have is v1 has 1 1 and v2 has 1 minus 1. So if we do this particular formula, we expand it. So what we are going to get is v11 multiplied by v21 plus v12 multiplied by v22. v11 is 1, v21 is 1 plus v12 is 1, v22 is minus 1. This comes out to be 1 minus 1 equals to 0. Since the dot product is coming out to be 0, therefore these vectors v1 and v2 are at 90 degree. This is what it is simply written here. Now, can we have three mutually orthogonal vectors in a two-dimensional vector space? So the general question is, can we have n mutually orthogonal vectors in a n minus 1 dimensional space? In a n minus 1 dimensional space. And the answer is no, we cannot have that. Why? Why we cannot have these many number of orthogonal vectors, mutually orthogonal vectors? The word is very important. The phrase is very important. It should be mutually orthogonal vectors. In such a scenario where the dimension of the space is less than the number of mutually orthogonal vectors that are desired. It is not possible. Why? Because mutually orthogonal vectors are also linearly independent vectors. And any set of linearly independent vectors forms the basis for the vector space. Okay, so if I have a two-dimensional space and I'm saying that can we have three mutually orthogonal vectors in this, we cannot have. So why? Because if we have three mutually orthogonal vectors, then these are linearly independent, and if they are linearly independent, then that means they form the basis. They form the basis. Now, basis for 2D vector space can have at most two vectors. So this is very important. Basis is any set of linearly independent vectors within that space. So I have a 2D space, 2D vector space, then I can have at most two vectors which are linearly independent and they will form a basis. So we can have any number of bases within for a particular vector space. So if we have more than two mutually orthogonal vectors, that this means that the basis has more than two vectors. So it has three vectors. So three vectors cannot form the basis for two-dimensional space. They will form the basis for three-dimensional space. Therefore, we should always keep in mind that a 2D space vector space cannot have three mutually orthogonal vectors. And in general, a n minus 1 dimensional vector space, or let's say n dimensional vector space, cannot have n plus 1 mutually orthogonal vectors. It is not possible. So this is a quick summary on why we cannot have. Orthogonal vectors are linearly independent. Linearly independent vectors forms the elements or forms the basis of the vector space, and the cardinality of the basis is always equal to the dimension of the space. Cardinality means the number of elements in a set, and basis is a set of vectors. Basis is a set of vectors. So for a 2D vector space, we will have a basis with two elements, and it the number of elements is always equal to the dimension. So 2D space will have a basis having only two elements. N dimensional space will have a basis with n elements. So that is how it works. So this is what it is. Now, for three-dimensional case, if let's say we have three vectors v1, v2, and v3, and now we want to check whether these vectors are orthogonal or not, then we check the dot product of each of the vectors. And instead of just looking into the graphical representation, from where if we know that these three x, y, z axes are mutually perpendicular to each other and the vectors are parallel to these three axes, then we can say that the angle between the vectors are 90 degree. But in case we do not have this particular kind of information or doubt, then simply go for the dot product. And here we find the dot product of v1 with v2, v2 with v3, and v3 with v1. Why this is needed? Because we want mutual orthogonality, mutually orthogonal. Okay, why we want that? This we will see in the lecture where we will discuss what is the basis and how the basis is formed. So in a three-dimensional space, we have three vectors v1, v2, and v3. For this particular set of vectors to be an orthogonal set, these conditions must be satisfied. That is, all vectors are perpendicular to each other, and this particular condition is called mutually orthogonal vector, mutual orthogonality. So all the vectors, that is v1 has a 90 degree with v2, and v2 and v3 have 90 degree between them, and v1 and v3 also have 90 degree between them. So this is what we say, that all the vectors are orthogonal to each other. Now the same question, can we have four mutually orthogonal vectors in 3D? The answer is no. The concept is the same, that in n dimensional vector space, we cannot have n plus 1 mutually orthogonal vectors. Why? Because mutually orthogonal vectors will be linearly independent to each other, hence they will form the basis for the n-dimensional space, and n-dimensional space can have at max n elements in its basis, cannot have n plus 1 vectors. So this is what it is. Can we have two mutually orthogonal vectors in a 3D space? Yes, we can have. So this is the reverse case of the above part. In the above part, what we are saying is that the number of mutually orthogonal vectors is more than the dimension of the space, which is not feasible. But the second case is feasible. That is, if I have a three-dimensional space, so can I have two mutually orthogonal vectors? Yes, I can have. So similarly, if I have a four-dimensional vector space, and if someone asks me that can I have three mutually orthogonal vectors? Yes, we can have. Can we have two orthogonal vectors? When we have only two vectors, then there is no purpose of saying mutually orthogonal, but okay. Two orthogonal vectors, then again we can say yes. So we can have lesser number of set of orthogonal vectors which is have less number of elements than the dimension of the space. So that is what it is. A 4D space can have orthogonal vectors with three element, a set of orthogonal vectors having three vector elements or two vector elements, and they will be representing a subspace. They will be representing a vector subspace which is lying within that particular space in which they are existing. So in a 3D space, let's say in a 3D space, we have two mutually orthogonal vectors, then they represent the basis of a plane within a three-dimensional space. So this can be three-dimensional space, and this represents the basis for the two-dimensional space within that. So this is all it is. So in Summary, we say that two vectors are orthogonal if the angle between those two vectors is 90 degree. The important condition is that both the vectors should be represented within the same coordinate frame. To check mathematically whether the vectors are orthogonal or not, then we find the dot product of those two vectors, and 0 is a vector which is orthogonal to every vector. Okay, and then the orthogonal vectors are linearly independent vectors, and the set of linearly independent vectors always forms the basis for the vector space, and the number of linearly independent vectors that we can have, mutually linearly independent vectors that we can have for a space, is equal to the dimension of the space, and therefore the number of mutually orthogonal vectors within a set that we can have is always at max can be equal to the dimension of the space. So this also links how the orthogonality will lead to finding the basis for a vector space, how the property of orthogonality will lead to finding the basis for any particular vector space. So that's it for today. Thank you.